Hi everyone, my name is Nadia Sitas and I'm from the Center for Sustainability Transitions at Stellenbosch University. This is just a quick video to introduce you to causal loop diagrams. And causal loop diagrams are techniques to map out the feedback structure of a system, identifying reinforcing or balancing feedback behaviors. And these causal loop diagrams are highlighted in chapter 26 of this handbook. In the section of dynamical systems modeling. And so this quick video is just an introduction to how causal loop diagrams can be a useful tool for systems thinking and understanding where you might want to intervene in a system. So causal loop diagrams are relatively simple. And so what you need if you are exploring this method is imagination and logic, so engaging both your left and right parts of your brain. You also need knowledge of the system that you want to work in, and this could be from if you've already done a conceptual social ecological systems map of your system, or you've collected a whole lot of data on various different relationships between variables in your system. Those are good starting points. For this exercise, if you just want to practice some paper and some pens to sketch out the different relationships. And then there are some online tools or software. So Kumu is one. There are a variety of others that can really help you visualize some of the relationships between different elements of your system. And so the schematic there around understanding causality just shows you some of the relationships and feedbacks that may exist in different systems. So causal loop diagrams also require you to engage kind of the thinking tools of a systems thinker, which have also been highlighted in other chapters, especially the introductory chapters, which highlight social ecological systems thinking. And essentially, this is about moving from understanding isolated parts of a system to looking at the interconnectedness of various different elements. It moves from linear thinking to more circular or relational thinking. It also moves from thinking in silos to understanding how emergence happens within systems. It gives you a much more holistic understanding of a picture, so putting together all the different parts to understand the whole. It also moves from just analyzing separate components to more of a synthetic understanding of the system and really thinking of things in a much more relational way and not isolated parts of the system. And a lot of the information was from this really cool tool. I've provided the website there, which has just highlighted a lot of these different tools of a systems thinker in a very accessible way. So systems thinking requires a shift in mindset, as I've said, to more relational thinking. And the fundamental principle of this shift is that everything is interconnected. So we talk about interconnectedness not in a spiritual way, but in a relational way. And it's really useful for understanding how different components of a social ecological system are connected. And essentially everything is reliant upon something else, especially if we think about human nature systems reliant on things for survival. So humans need food, air and water to sustain our bodies, and trees need carbon dioxide and sunlight to thrive. So everything needs something else, often a complex array of other things in order to survive. So inanimate objects are also reliant on other things. So a chair needs a tree to grow to provide its wood, and a cell phone needs electricity distribution to power it. So when we say, or when people say everything is interconnected, from a systems thinking perspective, we're defining a fundamental principle of life. So from this, we can shift the way that we see the world from a linear, kind of structured, mechanical worldview to a much more dynamic, relational, interconnected array of these different relationships between parts of the system and feedbacks. So a systems thinker uses this mindset to untangle and work with the complexity of life on Earth. So in general, synthesis refers to the combining of two or more things to create something new. And when it comes to systems thinking, the goal is synthesis as opposed to analysis, which is the dissection of complexity into manageable components. So analysis fits into the mechanical and reductionist worldview where the world is broken down into parts. But as we know, all systems are dynamic and often complex, and therefore we need a much more holistic approach to understanding certain phenomena. So the synthesis is about understanding the whole and the parts at the same time, along with the relationships and the connections that make up the dynamics of the whole. So essentially, synthesis is the ability to see the interconnectedness. From a systems perspective, we know that larger things emerge from smaller parts. So emergence is the natural outcome of things coming together. In the most abstract sense, emergence describes the universal concept of how life emerges from individual biological elements in diverse and unique ways. And emergence is the outcome of the synergies of the parts. So it's about non-linearity and self-organization. And we often use the term emergence to describe the outcome of things interacting together. So a simple example of emergence is a snowflake. It forms out of the environmental factors and biological elements. And so when the temperature is right, freezing water particles form beautiful fractal patterns around a single molecule of matter, such as a speck of pollution, a spore, or even dead skin cells. So conceptually, people often find emergence a bit tricky to get their head around, but when you get it, your brain starts to form emergent outcomes from the disparate and often odd things you encounter in the world. So this other example of how a caterpillar turns into a butterfly, there's nothing in a caterpillar that tells you it will be a butterfly. So the emergent kind of outcome of this metamorphosis isn't kind of the sum of the parts that you would look at when studying caterpillars. So since everything is interconnected, there are constant feedback loops and flows between different elements of a system, and we can observe, understand, and intervene in feedback loops once we understand their type and their dynamics. So the two main types of feedback loops are reinforcing and balancing, and what can be confusing sometimes is a reinforcing feedback is not usually a good thing. So this happens when elements in a system reinforce more of the same, so such as population growth or algae growing exponentially in a pond. And in reinforcing loops, an abundance of one element can continually refine itself, which often leads to it taking over. A balancing feedback loop, however, is where elements within the system balance things out. So nature, you can observe this in nature through predator-prey relationships. So if you take out too much of one animal from an ecosystem, the next thing you know, you have a population explosion of another, which is the other type of feedback, which is reinforcing. So understanding feedback loops is about gaining perspective of causality, how one thing results in another thing in a dynamic and constantly evolving system. And this, we know, all systems are dynamic and constantly changing in some way. And that has been explained in earlier chapters of the handbook. And so cause and effect are pretty, they're common concepts in many professions and just in observing life. And we often try to teach our children this at a very young age. And causality as a concept in systems thinking is being able to decipher the way things influence each other in a system. So understanding causality leads to a deeper perspective on agency, feedback loops, connections, and relationships, which are all fundamental parts of systems mapping. So systems mapping is one of the key tools of a systems thinker and has been, highlighted in a number of the other chapters. And there's some examples of how you might want to map a system. And there are many ways to map a system, from cluster mapping to complex kind of feedback analyses. But the principles, or the fundamental principles and practices, are universal. You want to identify and map the elements of the things within a system to understand how they interconnect, relate, and act within these complex systems. And once you've done this, you can start to have interesting insights that can be used to develop any kind of intervention, amplification, shifts for making decisions that can dramatically change the system in a number of different ways. And these can be indesirable or possibly sometimes have unintended consequences depending on who is making those decisions or interventions. So this is an example of causal loop diagrams, which this tutorial is about. And you don't have to look at the details because we'll go through it step by step. But essentially, this is an example of the outcome of what a causal loop diagram would look like. And there's a reference there if you would like to look at the paper. And so this was added just to demonstrate that a causal loop diagram can be as complex as you want it to be, depending on, you know, your target audience or the intended use of it. And so how you bound the system will often be reflected on the causal loop diagram. And so for more understanding on how you might want to bound a system, you can look at some of the examples on system scoping from earlier chapters in the handbook. And so these examples are both causal loop diagrams capturing population growth. So one of the first things to think about in relation to causal loop diagrams is causality, and this refers to the relationship between two variables. So A causes B, and as you can see in the top right diagram, another way to put it is that changes in B are caused by changes in A. And so a concrete example that we can start building on is funding for conservation activities cause some changes in the ability to implement conservation activities. And the same thing with the workload of conservation practitioners. So it causes some changes in whether or not people are able to implement conservation activities. And the direction in which those changes occur is indicated by the polarity. So that's the second element of causal loop diagrams. And the polarity can either be positive or negative. So for example, if A and B change in the same direction, whether they increase or decrease, then the polarity is positive. So you can see there's a plus sign indicated in the diagram on the arrow. And if two variables change in the opposite direction, such as C and D, then the polarity is negative. And you can see that with the minus sign on the arrow linking the two variables. So if we go back to our example, the workload of conservation practitioners changes the ability of conservation activities to be implemented. And increases in workload decrease the ability. So therefore the sign is negative. So if we look at the remaining two variables, funding for conservation, as funding increases, the ability to implement conservation activities also increases because those variables move in the same direction, and then the polarity is positive. So the central element of a causal loop diagram is the feedback loop, this is one of the main reasons to begin drawing causal loop diagrams, because it helps you identify those dominant feedbacks in a system and understand potential intervention points. And so what feedback loops denote is that there are changes in the system that catalyze a cascading effect through other variables. And this effect either reinforces or balances the initial change. So on the left-hand side, you'll see one type of feedback loop, and on the right-hand side, you'll see a slightly different one. And in practice, this can look quite messy, as you can see in the bottom diagram, but we can go through some examples to better understand them. So the first type of feedback loop is a reinforcing loop, and this signifies an amplifying effect. So sometimes it's called an avalanche effect. And as we know, there can be vicious cycles and virtuous cycles. So reinforcing loops don't necessarily denote positive or negative consequences. But if we look at the relationship between A and B, we can see that both of the feedback loop arrows are positive, which means that it's a reinforcing loop. And as an example of this around conservation awareness, we can see that the awareness participation loop. So as conservation awareness increases, so does the participation in conservation activities in this hypothetical example. And as more people participate in conservation activities, overall conservation awareness also increases. So you can see this is an awareness loop, and in this case, a virtuous desirable cycle. And so the other type of feedback loop is a balancing loop, and balancing loops are characterized by dampening effects. So much like a seesaw, as you see in this picture. So in this case, if we look at the top right corner, the relationship between C and D is positive in one direction. This relationship between C and D is negative in the other direction. And because there's not this amplifying effect that we were describing earlier, we call this a balancing loop. And building on the same example, I elaborated on the conservation participation and created a loop. And as you can see, one key trick to figuring out whether this is a balancing or a reinforcing loop is whether there's an even number of minuses or not. So if there's an uneven number of negative polarities, then the loop is balancing. So that is a shortcut to understanding whether or not it's balancing or reinforcing. So moving on to the next element of the causal diagram is you can have delays, and the delays signify the effect that A causes on B is delayed by some time element. In a causal loop diagram, this is symbolized through those parallel lines that you can see cutting through the arrow between A and B. And it's often the case that balancing loops are self-regulating and therefore experience delays. So the delay sign indicates delays in interaction. So as an example, an increase in the population over time will increase the number of birds. And as an example, this time from bush encroachment, as you can see, there's one delay between woody plants and tree maturity. And if we think about this conceptually, the relationship between woody plants and mature trees takes time. And so there can be a delay of several years. One final element of the causal loop diagram are these clockwise and counterclockwise loops and bows that you can see surrounding the B's and the R's in the direction. And these are a guide for reading the loops, especially when the diagrams can get messy. The clockwise and counterclockwise symbols helps you as the reader to understand in which direction you should follow the loop. And just so to summarize, to illustrate the different components that we spoke about earlier and their definitions, the first component is the variables. So you first have to identify the items of interest, and there are many methods that have been highlighted in the handbook for doing these different variables of interest. Then in the causal loop diagram, you have to determine how the variables are related, and that is defined by both the causality, direction, and polarity. And the central feature of the causal loop diagram is the feedback loops, and these can be reinforcing or balancing, and reinforcing loops can be vicious or virtuous. So sometimes the relationship between variables is characterized by delays, so A can affect B, but it might take some element of time before that's happening, and that can be also symbolized in the diagram. And finally, the loop symbols are an aid for reading the causal loop diagrams, especially as diagrams become more complicated and more variables and relationships are added. So that, in a sense, is a quick intro to causal loop diagrams. There are lots of available examples online. I mentioned earlier Kumu as a tool to help map out these different systems. So this is just a screenshot of what it will look like if you go on the landing page, and you can use some templates that they have. And you can see they've got a template for causal loop diagrams. And there you can start adding the various different variables of interest, the relationship between them, the polarity. You can add delays. Kumu doesn't necessarily have the clockwise, helps you understand kind of the direction that they're moving, but you can add a whole lot of different notes. And the best thing about Kumu is they've got a lot of explainer videos to help you get set up. So for further information, you can read chapter 6 of the handbook and also visit the Kumu site, and there they've got some examples, some worked examples and some videos for you to use. So I hope this explainer video was useful. And again, causal loops diagrams can really be useful for understanding what those important feedbacks are, for understanding where you might want to intervene in a system. Thank you.